I work in a field called flavor physics. Flavor has nothing to do with food here. It's just that us physicists like to try to be funny with our naming. So, flavor physics is an area of particle physics where we study the decays of particles. But these decays, they happen through one of the fundamental forces, which is the weak force. When these particles decay, their type of particle changes, but we don't call them types, we call them flavors. In flavor physics, we don't try to look directly for things. It's not something that we just go to higher and higher and higher energies and try to see something. No, flavor physics is a field of precision. So when we study these particle decays, we try to indirectly look for hints of this new physics that might lie beyond. My goal was to develop the theoretical tools that we actually use to predict these things. I study specifically the weak decays of quarks. They carry what we call a color charge. The color charge, we're funny with the naming. We call that because it's the charge that makes things interact through the strong force of nature. And there's three basic values. So we make this analogy with the red, blue, green kind of color system, the RGB. And what we see around are colorless objects. So really bound system, two things going around together. The things that I mostly looked at in my thesis were these colorless mesons, which is when we have a quark and an antiquark together. So then what you have is that the weak interaction makes one of these quarks decay. They change their flavor, but the colorful interactions between them persist. So to actually predict this weak interaction effects, we cannot forget about the colors there. The colors will shape how these interactions proceed. They will change the predictions. A funny thing about the strong force is that because it is so strong, we have a really hard time calculating it. So there's different ways to actually extract values of these things. And what I found out in general was that, well, it surprised me that indeed a lot of approximations have been made in the past. So first of all, a lot of flags had been raised that shouldn't be there. It was just a matter of being more precise. But on the other hand, some other places where we thought everything was fine, actually, no, there are some tensions there. So I see the work that I did as an important work to recognize where we still have to work on, how we can improve some things, and yeah, just getting a better picture of what the standard model looks like for flavor physics.